In this video, I'm going to talk a little bit about the seismic data that I provided for you in terms of what they are and how I come up with this kind of maps. And as you can guess, what you see here, these are fractures at different depths, right? I gave you 6 different depths. They are in millisecond, and the reason for that is because a seismic data is recorded in time domain. We send a wave down into the depths and we measure the reflection. Wave travels down and bounces back again to the surface from different horizons. We measure that one, and by knowing the velocity of the wave that propagates into the rock, we are able to calculate the distance. Okay, it's just very simple function. The data that I'm providing here, these are a time slice from 3D seismic cube. So what I have done, I applied a specific filter to ignore, the bedding, ignore, any kind of planar feature with a deep less than 80 degrees. So what you see here indeed is the planar features that has a deep more than 80 degrees. So they are fractures, right? So what you see here is the fracture network at the depth of 500 millisecond. So I'm gonna talk about how you can convert these milliseconds to the depths in a minute, but before, let's look at 2 different maps. As you see at this depth, so you have some concentrated fractures here. As you go in depths, right, you see the fracture pattern is changing, right? And the idea indeed is we want to digitize these fractures, as a line, and then come up with the Rose diagrams and compare how the orientation of these planar features, which are fractures, are changing with depths. Alright, so let's see how we can convert these milliseconds to depths, and how we can tie it with the chronostratigraphic chart. So I gave you a time depth chart. So there is 2 columns of data here that is representing two-way travel time, and the second column in this is true vertical depths. So I know for these different depths, okay, how much time is needed that the wave can get into that depth and bounce back to the Earth's surface, right? I don't want to get into the details, but this is called the TD chart, and what you can do, you can plot it in an XY Cartesian system. You can plot those numbers, and then which these are these orange dots here, and then you can fit a line for those dots and find the function of the line, right? So right now this is the function, and the y here indeed is representing the depths, and the x is representing two-way time. So if I have the function, I can actually apply for different depths. This is very simple method that we convert the time maps into the depth maps. So I know I have 6 maps from different depths. I have the function. What I can do, I can plot these numbers, which are in milliseconds instead of x, okay, and then I can calculate the y depths of the maps. So here, if I click on that, the function that you see here is exactly the same as function you have here. What I did, I just plugged these numbers into the function, and I obtained depths in feet and depths in meters. So the 500 millisecond map in time domain is the depth map at a depth of 738 meters, right, and so on. So right now, if I want to compare that one with with the chronostratigraphic chart right here. Let's check one more time. Okay, let's say 738, and indeed depths in, okay, here we have depths in feet, right? So the one that for 500 milliseconds is about 2,400 feet. So you have the depths in feet and 2,400. So we are looking to somewhere here. We are looking to the upper Cretaceous units. Okay, these two shales probably we are somewhere here. And as you go down, for instance, the last one, which is at the depths of about 22,000 feet, indeed that's gonna end up to the basement, right? In this area, the top of the basement, which is granite, right, is at a depth of 7,000 feet. So from 7,000 down to 22,000, it's all, Precambrian granites. Alright, this is the way that you can convert the maps in the time domain into the depth domain and compare with the chronostratigraphic chart.